Good morning, and to our friends joining us abroad, good evening. Welcome to Mirage Talks. Today, we welcome Senior Vice President, Head of Automotive Business at Valens, to enlighten us on the future-proof hardware for the software-defined vehicle. Gideon MT, thank you so much for joining us today. Let's get started.
Thank you very much. It's a pleasure to be here with you, and thank you for giving me the opportunity to present today. You might be asking yourself, future design hardware for the software-defined vehicle, what is this? Well, hopefully, if you stay with me through the end of my presentation, you will be able to have some understanding of this. I would like to start the presentation, if I may, with a short video. I think that is giving kind of a context of where the automotive industry is moving towards, how the future looks like. So bear with me with a second, and as I try to bring up the video to the screen.
It's now widely accepted that by 2030, mobility, especially in large urban areas, will be dramatically different from today. With transport seamlessly connecting people's lives, consumers will be able to get from A to B in a way which is cheaper, cleaner, safer. And our journeys will change to become productive and entertaining extensions of our day-to-day routines. With segments of the population, such as the young and the elderly, set to benefit from wider access. Let's have a look at just how the future might look. Instead of paying separately for fuel, tickets and travel cards, consumers will be able to buy integrated mobility contracts from new and different service providers. Not only will these providers benefit from a much wider sales opportunity, but the experience for the consumer will be easier and more joined up. Indeed, the concept of personally owning a vehicle and having to have a driving license to operate one may become redundant too. So that soon, the way a car functions will be unrecognizable. Electric, powered, autonomous, driverless, shared. A fully functioning digital environment.
Hi, Henry.
Hi, Katie. Ready for school?
A place of work. And a place to play. And with new entrants developing technology such as kinetic energy road harvesting, businesses are set to gain further from new revenue opportunities. New and previously unthinkable collaborations in and between sectors, not just how a car looks, but how it functions. And even when your car does malfunction, it will no longer need breakdown recovery to get it back on the road. The way we use public mobility will change too. Workspace. Whether passengers want to prepare for that 9 o'clock meeting, a bit of me time, or simply want filtered clean air. And when our cars are connected seamlessly to our digital selves, they'll be able to help coordinate our day-to-day lives and keep us fit and healthy too.
Morning, Henry.
Straight to golf, George.
Yes, please. Though I need to speak to the GP on the way. Holoport her in, will you?
Hello, George.
Hi, Alice. All fit and healthy, I assume?
I'm afraid not, George. Your blood pressure is above 140.
So no golf?
No, you'll just need to pick up your meds from the pharmacist beforehand.
And with the car able to place orders and send instructions, customers can pick up their prescriptions and the rest of their shopping seamlessly. Of course, this is just one version of the future. What is certain is that we are at the beginning of a truly transformational journey. We will see shifts in traditional business models. We expect to see two very different business archetypes existing side by side. So-called metalsmiths will continue to follow the current model of manufacturing ever more sophisticated hardware, the cars themselves. Meanwhile, an all-new archetype, the Gridmaster, will arise. The successful Gridmaster is not only a vehicle manufacturer, they also provide the platform for a variety of customer services. This means, as well as seamless travel from A to B, they can offer consumer-centric products and services by harvesting and using data at the customer interface. While each archetype will compete against a very different group of players, both will have an important role to play. By 2030, a new mobility services segment worth well over $1 trillion will emerge from products and services related to autonomy, mobility, and connectivity. We believe that future success will only come through an unprecedented degree of collaboration and through design and thinking across government and business. The future is exciting. The details are yet to be worked out, and collectively, we can build our model of mobility 2030. To find out more,
Gideon, can you unmute yourself?
Yes, I'm sorry. Okay, now can you mute? Okay, so I'll start again from the beginning of the speech. So I think the vision that we saw in the video is very exciting. It'll probably take more than 2030 until we see this really happening in reality. But the direction of cars becoming fully autonomous and driving new mobility services to the world is actually driving big changes in the automotive industry. To get a little bit of a perspective of this, let's take a look at the history of the automotive industry and the development of the passenger cars. Back at the end of the 19th century, when first cars were deployed, they were a masterpiece of mechanical engineering, right? And it took about 80 years until electronic components started to penetrate into the vehicles. And it took another 40 years for the electronic component to reach an influence of changing not just the environment of the driver, but also the engine and the way we drive cars. And electrical cars started to be deployed in the early 2000s, and it took another 20 years until electric cars mature to the situation where they are today in mass production, actually replacing the traditional engines. Together with the electrification of cars, new technologies which are enabling autonomous driving and enabling very advanced systems in the car are starting now to impact the way we see cars, and this is all leading towards fully autonomous vehicles in the, I would say, early 2030s, as we saw in the video. one of the things that is noticeable right in this chart is that the pace of change is accelerating. So the step in time for each generation of cars, from fully mechanical to start of deployment of electrical and electronic components until electrical cars are fully matured, and then we have automatic cars with some autopilot capabilities like we have in the Tesla models or in the Waymo car, through fully autonomous. The step in time is reducing from 80 years to 40 years to 20 years to 10 years. And this is another indication of the magnitude of the change in which the industry is going through. And this is actually shaking up the automotive industry. This is causing a huge change in the culture of the automotive industry, and also changing the notion of a car from being a masterpiece of mechanical engineering all the way to a masterpiece of computer engineering. Excuse me for a second, there is an issue here with my presentation. So I'd like to say a few words about the different levels of autonomous driving. I'm not sure that all of you are familiar with this, so it will be good just to get everybody on the same page. It is kind of an industry standard to define different level of autonomous driving from L0 to L5, 6 different levels. Level 0 is where you have no assistant at all. Level 1 is what is called feet off. So you can think of something like the traditional cruise control, which is giving you a constant speed. And then you can...
Gideon, your screen is not showing.
It's not showing? Okay, just a second.
There we go.
Let me know when you see it. Do you see?
Okay, I can see it, yeah. If you want to just put it in presentation mode.
Okay, so I wanted to just get everybody up to speed on the different levels of autonomous driving. So I said level 1 is called feet off, is where you have like the traditional cruise control, which is giving you constant speed. Level 2 is what is called hands off, and this is what you probably have in your car today, like an adaptive cruise control combined with a lane detection, which is actually enabling the car to move seamlessly in a traffic jam. Level 3 is what is known as the autopilot in Tesla, or Mercedes-Benz have recently announced this, and is giving you a highly automated driving capability, including the car performing bypass of other cars on their own. Level 4 is a fully automated driving, and level 5 is a fully autonomous one. And the key thing to notion here is that through those steps, the control over the car is moving from the driver, from the individual to the machine. Now, it's not only that the control, through the emerge of those processes, the control is moving from the individual to the machine, but also the software level and the complexity of software is increasing. The industry today is somewhere between level 2 and level 3. The more advanced car manufacturers that I've mentioned are already deploying level 3. Most of the cars that are coming out of the manufacturing lines today are at level 2. This is where we are. And then I said the trend is enormous increase in software complexity to be able to move from one step to another. This enormous increase in software complexity is actually forcing big change on the automotive industry. Automotive OEMs are very challenged with this change. They are investing a lot to build up software capability to recruit software engineers, and to be able to deploy the complex application that they need to deploy. Maybe we'll take a look at a few of the key technology trends which are driving and forcing this huge investment in software development. The first one is called connected vehicles. So cars today and definitely in the future will be more and more connected. First of all, they need to be connected to the cloud, to the internet, to be able to deliver added value services to the passenger, but also to deliver important information regarding traffic conditions, weather conditions, etc., into the car. Cars are not only connected to the cloud, they will be connected also to the infrastructure of the road. So in the future, the information regarding speed limits or hazard on the road or changes in infrastructure, etc., will all be communicated from the road signs, from the stoplights, from the road infrastructure into the car. And of course, car needs to be communicating with each other, right? As car becoming more and more autonomous, they will be communicating with each other, giving warning to each other with respect to the distance, whether they are now bypassing from the right or from the left, etc. So all this communication, right, requires a lot of hardware infrastructure and also sophisticated software to manage it. The second trend is the human-machine interface. And we see here a transition from mechanical interfaces like switches and buttons to touch screen. I think this is very much deployed already today. And probably most of you have touch screens in your cars. But the next thing which we are moving to is what is called gesture recognition. And gesture recognition is something that will enable you to start a car or stop a car or open a window, open a door, and get all kind of reaction from the car just by a movement of your hand and your head. And the implementation of this is involving inside cameras in the car, which is monitoring the driver and the passenger, and also, of course, sophisticated software to enable this. The electrification of vehicles is the third one, which is driving big changes in the industry. The electrification of the vehicle is not directly impacting the need for sophisticated software, but it is creating a big change in the culture of car manufacturers. The electrification is changing the balance, right, between mechanical engineering and electrical engineering in the car, and it's also accelerating the development of new companies. We've mentioned Tesla in the US, which is a leading one, and NIO in China is another one, Rivian in the US, the electrical truck company. And the change in culture that they do is causing the development cycle of a car to be much shorter, which is again pushing more application to software than to hardware. Another thing that the electrification is doing is changing the fundamental architecture infrastructure of the car from the inside, and this is actually enabling the required architecture for the software-defined vehicle. Excuse me, for the software-defined vehicle. We'll touch on that in a minute. And of course, the fourth and most dominant trend, which is requiring huge amount of software development, is the autonomous driving itself. Not just software development, but also artificial intelligence to be able to manage the cars of the future. So all of this is actually creating a new creature, a new animal, which is hitting the road, which is the software-defined vehicle. And the software-defined vehicle is a car which may look similar to the car that you see today, but inside it is very different. First of all, it has a lot of ADAS, Advanced Driving Assistant system deployed in it, which is enabling certain levels of autonomous driving, as I've described before. And this, of course, requires different layers of sophisticated software. The second thing is this car has deep cloud integration. So it's constantly connected to the internet constantly delivering services to the passengers and also giving the car itself layers of cybersecurity and things which are required to operate safely. So those two elements are very loaded with software. And then, of course, the car needs to be able to do what we call over-the-air updates. And over-the-air updates, just like what you do with your phone, is actually a constant update and fix of your different application, either to give new features or to correct safety problems. And the car, actually the software-defined vehicle, is becoming more like a smartphone on wheels than the old mechanical animal that it was when it was born. So this is, in a nutshell, what the software-defined vehicle is and what is driving it. If we take a little bit of a deeper dive under the hood, and I know that most of you are probably not engineers, so I will try not to make it too complex, but the thing to understand is that under the hood, there are several layers of implementation. Some of them is hardware. HPC stands for high performance computing. So some of it is hardware. The core is a high performance computing engine. And on top of that, you have several layers of software, operating system, and then interfaces to the unique vehicle services layer. And on top of it, the different software application responsible for autonomous driving, responsible for cockpit management, for all the advanced infotainment system, and responsible also for managing the car bodies and utilities itself. And of course, all of it needs to be connected to the cloud.
Slide number 4, the 6th level of autonomous driving. I don't know which slides you're presenting, but we see slide number 4.
So it hasn't moved from slide number 4?
No.
So have you seen this slide? Do you see slide number 5 now?
We actually can't see anything right now.
I think it will be better to see it in edit mode, and then we'll be able to see better. Okay, well, now we can see it.
Yep.
Let me stop share. Do you see slide number 5?
No, I think it's best if you keep it in edit mode.
Do you see now slide number 5?
Yes.
Okay. So I was talking about the connected vehicles, right? The need for the changing in the driver machine interface, the electrification of cars, and the autonomous driving. All of that giving the enormous software increase in the cars. And then was talking about the software-defined vehicle itself, right? Where the key ingredients of the car now is the advanced driving assistance system, which requires a huge complex software to deploy, the connection to the cloud, right? For added value services and for cybersecurity and safety. And then the need to be able to do over-the-air updates like you do for your smartphone. So the software-defined vehicle is actually very much, it's more similar to a smartphone on wheels rather than the old mechanical creature that it was when the car was first established. And if we look under the hood of the software-defined vehicle, and as I said, I don't want to get too much into engineering details, but it's important to understand that there are several layers. right? There is the fundamental layer of the hardware, where you have HPC, stand for high performance computing. You have a strong high performance computing engine with different layers of software on top of it, the operating system, the interface to the vehicle services, and then the key thing where most of the software development effort is to develop the different application, the autonomous driving application, the cockpit, which is controlling all the advanced infotainment in the car, and then the application which are controlling the body, the operation of the car, the speed of the car, etc. Of course, all this need to be connected to the cloud, right? And we spoke about the over-the-air update, right? So those applications which are controlling most of the functions of the cars can be updated over the air in a similar way that your smartphone application are being deployed. If we look in the car, what does it mean inside the car? Somewhere in the center of the car, there is a central strong compute engine, which needs to be connected to the different sensors around the car, the camera, the radars, which are giving it information regarding what is happening in the environment, and of course, the connection to the cloud. And one of the key things to understand is that this connectivity from the sensors to the central compute, and also from the telematics unit, which is connecting you to the cloud, to the internet, to the central compute, this connectivity needs to be of high bandwidth, high speed, and very resilient connectivity. The car environment is pretty rough, unlike your home environment or computer room environment. In the car environment, you have many interference. You have electromagnetic radiation, which is coming from the inside of the car and also from the environment. The car is driving in different weather conditions, which is again bringing a challenge. This is why the resilience connectivity is of high importance for the, I would say, foundation of the hardware, which is enabling the software-defined vehicle. So far we spoke generally about the industry and the software-defined vehicle, and I'd like to take a few minutes now and to tell you a little bit about Valens, the company I work for, and how are we connected to what is happening in the automotive industry. So first of all, a few words about Valens. Valens is an Israeli semiconductor company, was established in 2006, about 300 employees, most of them in Israel in the headquarters, but we also have presence around the world in all the major automotive hubs, in Japan, in Korea, in China, in Germany, and in the US. We are driving innovation and technology, and we have more than 100 patents registered to date, and we are focusing on high performance connectivity, what I've just described as a very important foundation for the software-defined vehicle. Valens is operating in two main markets, in the audio-video market and in the automotive market. And since September 30 of last year, Valens is a public company, traded on the New York Stock Exchange. You can see our CEO, Gideon MT, ringing the bell of the New York Stock Exchange on September 30. For the next slide, I have to try again and go into animation mode. Let me know if you can see it. Do you see slide 10?
It's still dark.
No, we cannot see it.
You cannot see it, okay. I'll take it out. Do you see it now?
Yes.
Okay. So as I said, we are operating both in the audio-video market and also in the automotive market. As you can see on the title, our slogan is pushing the boundaries of connectivity everywhere. So let me just explain this slogan for a little bit. Connectivity is electrical connectivity, right? Has a few dimensions. There is the bandwidth, which means how many gigabytes or megapixel you can transfer to over what distance can you transfer this? What is the error rate or how reliable your connectivity is? What is the latency? How much delay do you have between the source and the destination? And then, of course, what is the total cost of operation of the solution that you are providing? And when we say that we push the boundaries of connectivity everywhere, we are very proud that our solution is actually giving the best performance across all those dimensions, right? Unlike some competitive solutions that are giving you relatively high performance in one or two dimensions, the advantage of the Valens technology is that we're actually covering all dimensions in an optimal way. And we are enjoying success with this technology. One of our famous customers is Daimler, Mercedes-Benz, and in Mercedes-Benz we are enabling the connectivity of their very advanced MBUX infotainment system. You may or may not know that the slogan of Daimler is the best or nothing, and we are very proud that they have chosen us as the infrastructure for their infotainment system. And we are in mass production on the road with all of Mercedes-Benz vehicles. I think this is something which is a proof of the resilience of our technology, which, as I said, is essential for the future software-defined vehicle. Another example of success is with a company called Stoneridge in the US, where we are deploying a solution for a rear view camera for semi-trailers. Again, this is a very challenging requirement, delivering high quality video from the rear of the truck to the front without delay and without any interference. Of course, for safety reason, when the truck is driving backwards, you cannot afford any glitches or even a fraction of a second delay, which is a big hazard. Our technology is the only one which is actually able to deliver this zero latency and zero error for such a long distance. And again, that's a proof of the resilience of it. Basically, we are a semiconductor company, and that means that what we are delivering to our customer are semiconductor chips. You might have heard recently, it was in the last year, all over the media that automakers are suffering from supply chain issue with chips, and many automakers were forced to reduce production because of the lack of availability of certain devices. We're very proud that we were able to supply our customer fluently through those times, but I think the key point I want to make here is that cars are becoming more and more dependent on semiconductor and on electronic devices. And again, this is something which is essential to secure the future of software-defined vehicles. How are we connecting to the software-defined vehicle? Do you see slide 18?
Yes, but before that, one question.
Yes.
Connectivity in the Mercedes vehicles or in the trucks, is it based on standard automotive protocols, or you need your proprietary protocols?
The connectivity is based on our proprietary protocol in the Mercedes and in the truck, which is in our future generation is now defined as a standard by the MIPI Alliance. So the MIPI A5 standard that was recently defined is based on our technology.
Okay, thanks.
Okay. So how are we connected to the software-defined vehicle? When you look into the future car, you see a lot of sensors, right? Cameras, radars, surround view cameras, front radar, lidars, back cameras. All of those need to be connected to the central compute unit to be able to enable the car to function fluently. And what we are focusing on is giving this resilient connectivity between all those different sensors to the compute unit of the car. And here I really need to show the animation to explain this slide. Let me try once more. So do you see slide 20 now?
Yeah, yes, we do.
And what about now?
Yes,
You do see slide 20?
we do.
Okay, great. So the current deployment of electrical compute unit in the car is very distributed. The car is not yet at the software-defined vehicle situation where you have one central compute unit connected to all the sensors around it, and the deployment is distributed. In order to implement this future hardware which is required for the software-defined vehicle, you need resilience connectivity to be able to connect over relatively long distance the sensors and the compute. And this is actually what we are enabling. The key thing here is not just to give the high bandwidth with the zero latency, but also, as I've explained earlier, to overcome the electric radiation interference which exists in the car and in the car environment. And this is something that we are doing in a very sophisticated and efficient way. Unlike other technologies which are trying to shield you. Do you see slide 21, by the way?
Yes.
Yes, unlike competitive technology which are trying to shield you from the interference, our technology is actually taking in the interference and canceling it. So we have sophisticated mechanism which is learning the profile of the noise of the interference and canceling it and giving very high resilience to the connectivity in the car. Okay, so this is Valence. This is what we do to enable the future-proof hardware for the software-defined vehicle. And let me conclude the presentation with another short video. Which will summarize the capabilities of our technology.
For years, car makers have been racing each other on the road to autonomous driving. And to their credit, they've made big progress. Since the race began, they breezed past level 1, driving assistance, and they bent the corner past level 2, partial automation. But something unexpected has happened. It seems they've lost their momentum. They've stalled, each of them, around level 3 of autonomous driving. So they try again and again, driving around this familiar, worn-out track. They collect their coins, but make little progress. And after each race is done, they return to their garages and think, what does it take to level up on the road to autonomous driving? Well, for autonomous driving to work, cars need systems made of sensors linked to ECUs. In terms of sensors, cars are using more and better ones than ever before. And it's not just cameras, but radars and lidars as well. These need to be able to sense everything around you, identifying pedestrians, red lights, and nearby vehicles. So car manufacturers have been rushing to jam these sensors into their vehicles, and they spend the coins they've gathered along the way on the newest and greatest systems the market has to offer. Not surprisingly, cars on the road today have more ADAS sensors than ever before. Some have over a dozen and counting, and it's not just the quantity, but the quality as well. Sensor manufacturers are creating 15 megapixel cameras, low angular resolution radars, and high frame rate LiDARs. Of course, these sensors produce a ton of data, so cars need to have incredible electronic compute units, or ECUs, capable of receiving and processing that data at lightning speed. Or in other words, cars need bigger and faster brains to make decisions, to accelerate, to stop, or to swerve. Today's cars also have more powerful ECUs than ever. Some are capable of processing trillions of floating point operations per second. And yet, despite all this, the cars sputter and stall, mostly unable to beat level 2. So, what's going wrong? What is stopping the industry from reaching the next levels of autonomous driving? Or in other words, what's the missing link? The missing link is the link itself. That's right, the link connecting the state-of-the-art sensors to the state-of-the-art ECUs is kind of, let's call it, underleveled. Which is why the lens technology is such an important development for the industry. We've created a solution that will finally allow automakers to level up their in-vehicle connectivity, and with that, to level up their autonomous driving systems. Our technology offers a lot of upgrades over others in the market. It supports high bandwidth for those double-digit resolution sensors being implemented. It transmits the data with near zero latency to ensure that there's no delay between the identification of a pedestrian and the slamming of the brake. It's resilient, meaning it operates with zero errors or data loss, even in the harsh electromagnetic environment of the car. Perhaps most challenging of all, it enables architectural flexibility, letting automakers place sensors and ECUs where they need to be without distance limitations. It offers redundancy so that there can never be a single point of failure, and it runs primarily over hardware, paving the reliable physical foundation for the software-defined vehicles of the future. And bonus, it does all this while lowering the total system cost. Our chipsets are already on the road in vehicles around the world, including Daimler's Mercedes-Benz. Valens is first on the market with chipsets that comply with MIPI A-PHY, the global standard for long-reach in-vehicle connectivity. The MIPI ecosystem is growing fast, with leading automotive players developing systems based on this standard. Valens technology is nothing short of a game changer for an industry on a quest to level up.
Okay, thank you very much for listening. This concludes my presentation, and I'm happy to take any questions if you have.
Thank you, Gideon. You can either unmute yourself for the question, or of course, as always, send your message to the chat box.
Hey, Gideon, this is Eli. Thank you for the presentation. I have a question with regards to the connectivity to the cloud. As the software-defined vehicles generate such a vast amount of data, and some of the data is processed within the car, some, as you mentioned, is connected to the cloud. Where do you see edge compute infrastructure in this high-level architecture?
So I think that I've mentioned it, right, that the car itself will have several high-performance computing engines in it, right? So definitely the needed compute performance in the edge, in the car, right, is going to be there. I think the challenge is not so much with the power of connectivity, it's not with the power of compute, it's with the connectivity. And this is why the deployment of 5G networks around the world is accelerating, because the 5G networks will enable the bandwidth to transfer the enormous amount of data which will be required between the cars and the cloud.
Thank you.
Any more questions before we close?
Yeah, I have one quick question. This might be kind of a basic question, but the technology you guys are producing, is it a new type of cable that connects the sensors to the ECU, or is it just a different way of communicating within the existing hardware that is available today?
No, so it's not the cable. We use the cable, right? We give sophisticated connectivity chips, semiconductor devices that are connected in both ends. So let's take, for example, a sensor, a camera, right? So you have a camera on one side of in the front of the car, and then near this camera, you have a transmitter, which is our chip, which is transmitting the video data coming from the sensor over a cable to the ECU. On the ECU side, we have another chip, which is the receiver, which is receiving the video that we have transmitted over the cable and handing it over to the ECU. Okay, so when we say we enable the connectivity, we give like the two ends of the cable is the channel where the data is flowing through. You need to collect it in one side, transmit it over the cable, and then unpack it in the other side and hand it over to the ECU. That's what we do.
Got it. Thank you very much.
Well, on that note, on behalf of Paul Mirage and the Mirage Institute, Gideon, thank you so much for taking the time today to enlighten our Mirage tribe. This was wonderful. As always, Ellie, thank you for coordinating such a special Mirage talk. Thank you everyone for joining us today.
Thank you very much.